Hey again, folks. We've done many problems involving friction on ramps, but it's always been a constant amount of friction. Have you ever wondered what it would be like if the friction varied across the surface? Well, if so, I have the perfect problem for you. There's a worker here who is shoving a box up an icy plank where the coefficient of friction increases with the distance from the bottom of the plank. Our task is to verify this inequality shown at the bottom, describing the required initial squared velocity in order to get the box to stay at rest once it stops moving. Let's start with a free body diagram. The weight of the box will point straight down, and the normal force from the ramp will point in the plus y direction using this coordinate system I've set up here. As the box slides up the ramp, it will experience a variable kinetic friction which acts in the direction opposite to the motion. The only vector that needs to be broken into components is the weight, so let's insert alpha and get those cosine and sine components like this. The next order of business is determining how we can use the work-energy theorem to solve the problem. When the box comes to a halt, the final velocity will, of course, be zero. That means that the net work done on the box will be equal to this negative quantity. But what is the net work done on the box? Well, it certainly won't be constant because of that variable coefficient of friction, so let's use the integral definition for work. We have the force of kinetic friction and the sine component of the weight acting against the direction of the displacement. So we'll need to integrate the sum of those two along the x direction from the bottom of the plank to wherever it stops. Let's plug those expressions in now. We were told that mu is ax, so that can be replaced in our integrand. The normal force is balanced by the cosine component of the box's weight, so we can substitute that in as well. The whole expression down here at the bottom, this is the net force done on the box, which is equal to our previous negative kinetic energy. Before we integrate, let's eliminate some things and simplify this a little. We have the mass of the box on both sides, so that can be removed. There's also a g in both terms on the left, and that's a constant here, so we can factor that out. Additionally, let's multiply both sides by 2 to get rid of this 1/2 factor on the right-hand side. I'm not a big fan of working with negatives when we don't have to, so let's also multiply both sides by -1. And that's all the simplification we can do here. The integral is with respect to x, so it doesn't care about a or these trig identities that depend on alpha. So really, it's like we're integrating x plus 1. The integral of x in the first term will just become x squared over 2, and the integral of 1 from the second term will just attach an x onto the sine of alpha. We can save some time and just evaluate at this final endpoint only, since the other endpoint of 0 just makes everything go to 0 for that portion. In the end, we'll get this. Now, what we have here is helpful, but the inequality we're supposed to be verifying didn't contain any kind of x in it. We need to find a way to get rid of that. Let's resort to using the static friction. We know that If the static friction is greater than or equal to the box's weight along the ramp, well, then the box won't move. Let's insert the expressions for these quantities and take a closer look at this. Here we have negative mu times the normal force being greater than or equal to negative mg sine alpha. Since they're both negative, we can just eliminate those signs and work with positive quantities. Remember, the normal force was just mg cosine alpha. And since we have mg on both sides here, let's get rid of that and bring x back into the picture, since mu is equal to ax. But instead of just a generic x, we're working with the final x distance that the box travels up the ramp. If we divide both sides by a cosine alpha, we see that the final distance that the box moves up the plank has to be greater than or equal to this ratio here on the right. Otherwise, it won't come to a stop and it will just slide back down. Let's start with the minimum case here. We want the shortest distance that the worker can push the box in order to meet this requirement. We'll plug this ratio back into our expression and start simplifying. The a in the numerator of the first term here will cancel with one of the a's in the denominator because of the squared happening. And the same will go for the cosine. In the second term, these two sine alphas will multiply together, resulting in sine squared alpha. We can get a common denominator between these two terms here if we distribute the 2 inside. Notice that the 2 in the denominator is now gone in this first term, and the second term just becomes twice as big. But that's okay, because they share the same denominator. So let's go ahead and join those together. Now there's 3 total, and if we distribute the g back in, we get 1/2 of the inequality that we needed to demonstrate. This tells us the absolute minimum initial squared velocity that the worker needs to impart on the box in order to get it to stay put. But what about the greater than part? Well, here's a reminder on what we had before. We saw that in order for the box to come to a halt and stay there, the box needs to be pushed a distance greater than or equal to this quantity. How do we get that further pushing distance? Well, we can just apply a greater initial squared velocity. As long as the bare minimum is reached, anything larger than this will also work. So that's why the inequality from the problem description is greater than or equal to the ratio on the left. With that said, we've covered both parts of the inequality now and shown what was needed. I hope that this helped. Have a great night, everybody.